Hello, welcome back. We're now moving on to a new section, the measures of central tendency. So these are quantitative measures that explain characteristics of data. So then we can see where the data are centered. And we're going to be looking at the following ones: the arithmetic mean, the median and the mode, and then the weighted mean, the geometric mean, and the harmonic mean. So there's quite a few that we need to get through. But just before we start on these, we need to go through a couple of definitions. And the first one is a statistic. So this is just a measure that summarizes a set of observations. And descriptive statistics, they summarize the central tendency that we spoke about over there, and also the spread variation in our data. So with spread variation, we're going to be doing a class on measures of dispersion. And there we're going to look at how spread out the data is, how volatile the data is. And we're going to be looking at things like the variance and the standard deviation, which are going to measure the risk of the data. And then a population, we know what this is. This consists of all the members of a specified group. So for example, all of the shares on a stock exchange, that will be a population. And then a sample, that's going to be a subset of a population. So if we take 50 shares out of all of the shares on a stock exchange, that will be a sample of the population. And a parameter, this is a statistic that describes a characteristic of a population. It's easy to remember because we've got a P over there and we've got a P over there. So for example, if we work out the population mean, of course, it's a parameter because it's describing something about the population, or population variance or population standard deviation. Those are measures of dispersion that we spoke about just now, which we're going to be doing in detail in another class. And then a sample statistic, this is now a quantity computed from, or it describes a characteristic of a sample. So if we work out rather the sample mean, of course, that's then going to be a sample statistic. And most of the time we use sample statistics because, you know, the population information is just too much. So we normally rather use sample stats. Great, so let's get started then with our first measure of central tendency, which is something we know very well, the arithmetic mean. We just sum the observations, we sum up all the observations, and then we divide that by the number of observations that we have. So the sample mean, of course, is just going to be an arithmetic mean for our sample. So to work it out, it's got sample mean has got this symbol over here, X with a hat on. So then the way we pronounce it is X bar. So all we do is in the numerator here, we sum up all the values of the observations. So we know this sign over here, that is sigma, which means we sum up all of our observations, all of our X's over there. And then once we've done that, we divide that then by the number of observations we have there, the N. So if we take this little example here, nice and easy, we've got the return for top text common shares the last 4 years have been this. So what is the sample mean? So in the numerator, we just add up all of our returns, and then we divide that in the denominator by the number of observations. So we can see the sample mean is 5%. So this is what we call a time series mean, because it's the mean of time series data. So we've got the data over a certain period of time. But we also get what we call a cross-sectional mean. So this is the mean of cross-sectional data. So for example, if we take the sample mean of the returns of 50 shares in a share index, then we're going to get the mean return as an average across. So that's why it's called the cross-sectional mean, because we're going to get the average return of those 50 individual companies. Right. And then, so we can also think of the mean as the center of gravity of an object, because some values are going to be below the mean and some values are going to be above the mean. So the mean is like, we think of like as the center of gravity. And there is, though, a problem with the mean, because it's sensitive to extreme values, or what we call outliers. So for example, let's say in this year over here, the return wasn't 6%, but it was 100%. Of course, the mean is then going to shoot up, but that may have just been a once-off event. And then this mean for over those 4 years would actually paint a false picture. So the question is now, how can we deal with these outliers? And here is our answer. So as we said, an outlier is an extreme value, and it's usually a rare value in the population, but it may also be a recording error. And sometimes we can transform the variable. So for example, we can do a log transformation, which we're going to talk about in further down the line. Or we can even sometimes select another variable. But if we can't do this, there are 3 ways to deal with the outliers. I'm going to go through all of them one by one. So the first way to deal with them is the easiest. Just do nothing. So don't make any adjustments. Don't make any adjustments. And this is appropriate if the values are all correct and we need to reflect the whole of the sample distribution. Because sometimes excluding or altering these values may actually reduce valuable info. So the second option, what we can do is we can exclude the outliers. For example, we get this thing called the trimmed mean. So this is calculated by excluding, as we said there, excluding the outliers. So we're going to exclude a stated small percentage of the lowest and the highest values in our data set. And then we're going to compute a new arithmetic mean of the remaining values. So for example, if we do a 10% trimmed mean, we're going to exclude the lowest 5% and the highest 5% of the data. And then we're going to compute the mean of the remaining 90%. Good. And then the last way to deal with these is to substitute the outliers with other values. For example, we get something called a Windsorized mean. And this is calculated by assigning a stated percentage of the lowest values to one specified low value, and the highest values equal to one specified high value. So we are not excluding them. We are just changing the very, very low and the very, very, very high numbers. We're just changing them to another number. And then we're going to calculate the mean from the restated data. So for example, if we do a 90% Windsorized mean, we're going to set the bottom 5% of values equal to the value at or below which 5% of all the values lie. So this number here, this we call the 5th percentile. Now, it's not going to make much sense now because we're going to do this in the next class. But all we need to know for now is that we are not going to have very, very low numbers, because all the bottom 5% are going to be the same number because we're setting them to one specified low value. And then we do the same for the top 5%. We're going to, the top 5% of value, we're going to set the top 5% of values equal to the value at or below which 95% of all the values lie. So this we call the 95th percentile. And again, this will make more sense when we do the next class. But all we need to know for now is that then we do not have to worry about the very, very high numbers, because all of that top 5% of the numbers are all going to have the same number because we're setting the highest values to one specified high value. Good. So this means we can now move on to the next measure of central tendency, which is the median. And so what we all know what the median is, I think. So this is the value of the middle item or the midpoint of our data set when the items, they must either be in ascending or descending order. So if we've got an odd number of observations, then the median is just the middle number. So if we've got this example here, the annual returns of Northern Retail Common Shares over the past 5 years have been this. So what is the median? So I've put them here for us in ascending order, smallest to bigger, smallest to biggest. So all we need to find is the middle number, which is over here. There's the middle there. It's going to be that 8% over there. So the median is the middle number, which is our 8%. So this is now, there is a little formula we can use to find, the position of the median. We don't have to do it if we have a small data set, but if you've got a big data set, like 100 or something like that, then okay, odd number, let's make it rather odd number, let's make it 99, let's make it 99. If we got a 99 99 observations in our data set, then we can do something like this to find, where is the median going to be. So the median is the value of the item that occupies the n plus 1 divided by 2 positions. That doesn't make much sense, but if we do this little example, you'll see how easy it is. So the median here for us, we've got how many observations? We've got 5. 1, 2, 3, 4, 5. So 5 plus 1 there is 6, divided by 2 is 3. So we can see that the median occupies the third position, which is correct. 1, 2, 3. So why I put this in is because there was a practice problem where we had to do something like this. And this is a good time to mention that, it's very important for us to do all those CF Institute practice problems like we've spoken about before. But we're going to talk about that problem on the next slide. So if we have 99 observations, so of course 99 plus 1 is 100, 100 divided by 2 is 50. So if we have 99 observations, the median is going to be in the 50th position once we've ordered the data from smallest to largest. Great. So now, what about if we've got an even number of observations? Now the median is going to be the arithmetic mean of the 2 middle items. So in this example here, we've got the same information as before, except we've got now 6 years and not 5 years. So this is the only difference now. Now we've also got, in that 6th year, the return was 3%. So there's the 3% there, which wasn't there before. So again, if we arrange in ascending order, so now we've got an even number of observations. So with the median is going to be, the mean of the 2 middle items. So the 2 middle items are these 2 guys over here. So we need to take the mean of these 2 guys, which is going to be 7%. So our median is going to be 7%. So now, here's the little formula to work out, what happens if we've got an even numbered sample of however many items. Now, the median, it's going to be the mean of the values occupying the n over 2 and the n plus 2 divided by 2 positions. That doesn't make much sense. But if we do our example, we'll see it's not so bad. So for our example, the median occupies what? So how many observations have we got? What is our n? We've got 6 observations here. So it's going to be 6 over 2, which is 3. And then we've got 6 plus 2, which is 8 there, divided by 2, which is 4. Okay, so that's what I said over here. So the mean is the mean. So what we need to do is take the mean of the 3rd and the 4th positions. So there we can see the 3rd and the 4th position. So it's not so bad, this, because the first number is easy. It's just our sample size divided by 2. And then, of course, the next position must be the one after this one. So whatever this one is, we can just add 1. So to work out, the next one, we don't have to actually do this over here. We can just take whatever that is over there and then plus 1. And that'll give us what the second one is. And we take the mean of these 2. Right. So coming back to this practice problem that I was telling you guys about, I've got it ready in front of me. It was practice problem 14. And what we had to work out was the median of, and they had 50 observations. So what we had to do was take 50 divided by 2, which is 25. Okay, let me rather write it down over here. It was 25. Okay, and then the next number then must be 26. So if you take 50 plus 2 divided by 2, you're also going to get 26. So we had to take the mean of those two guys. And what they also threw in this example, I can't go into all the detail now because it'll take too long, but they also threw in a histogram here, and we had to use our knowledge of histograms together with the median to work out this problem. But you guys will come to that, because as we said, we're all going to do all of our practice problems. And just one last note over here about the median. One thing that's important is that it's less affected by outliers than the mean. Because if we stop there, for example, if this last number here wasn't 26%, but let's say it was 100%, then of course the median wouldn't be affected because we're only looking at the middle numbers, but the mean would shoot up very high because we now got this one outlier. So the median is it's less affected by outliers than the mean, but it does have a few problems because it does not use all the info from the data set. And calculating it can also be complex because we need to, arrange all the data from smallest to bigger, so that can be a bit of a mission. So just a practical example of where we often do see the median is in the property market, because, to work out the mean, sometimes we've got these outliers. Some properties are in the suburb might have done major renovations, and those properties are way up their value, and some houses are like being dilapidated, so their values have fallen way below. So all these distortions can distort the mean, but the median, we just take in the middle numbers, so that is often why in the property sector, we often use the median and not the mean. Right. And now we're going on to the next one, which is the mode. So we know what the mode is. The mode is like the fashion. Hey? So it's the most frequently occurring value. So if a distribution has one most frequently occurring value, we call it unimodal. If it's got two most frequently occurring values, then it's bimodal. And if it has three most frequently occurring values, that's now called trimodal. And what happens if all the values in a distribution are different? If they're all different, well, then we have no mode. So if we look at this data set, what is the mode? So what number occurs the most? Only 4% is occurring twice. So the mode is going to be 4%. No other number is occurring more than once. So the number occurring the most is 4%. That's going to be unimodal. There's only one most frequently occurring value. So this is going to be unimodal. So I just made a couple of notes here. So remember our histogram from some time back? The bin or the interval with our highest frequency, we call that the modal interval. So if we think back to that Riverside retail example where we did the histogram, remember where that interval, it was 0 to 5%. And we saw in that interval, the return occurred in that interval 4 times out of the 10 years, and that was the most. So that interval is the modal interval. If you go back, you can check it. And a data set, it can have only one mean and one median, but it can have more than one mode, like we've discussed over here. And the mode, interestingly enough, is the only measure of central tendency we have that can be used with nominal. And remember nominal, we did this in our first class. This is non-number data. It's the only measure where we can use nominal data. So I know this goes back a long time ago, but remember when we discussed nominal data, we used an example where we categorized investment funds into different styles. So we spoke about equity growth or equity value, or a fixed investment grade fixed income or non-investment grade fixed income. So if we've got a whole lot of different type of investment funds, let's say we've got 20, and the type of fund that occurs the most out of the 20 is equity growth. Then the equity growth style, that's going to be the mode. So we can't, for that example that I've just given us, that nominal data, we can't work out a mean or a median for that information, but we can see, which style occurs the most. Great. And now we need to look at the weighted mean. So this weighted mean, we're going to see this all over the place as we go through the curriculum. So it's an important little formula. So on the exam, they might not ask us to work it out in quants, but they may ask us to apply it in many other places in the curriculum. So let's have a look what it is. So the weighted mean of a portfolio's return, it's calculated from the returns, I beg your pardon, it's calculated from the returns on the individual assets, where the weight applied to each asset's return is the percentage of the portfolio invested in that asset. So it sounds complicated, but it's not. So this is the symbol for weighted mean. So the W is for weight there. So the weighted mean, all we do is we sum up here the weight that we've got in each asset, and X is the return of each asset. So as we said, sum up. So we do it for each and every asset that we have. So if we try the example, we'll see how easy it is. We've got Lebo has an investment portfolio, the following weighting. So she's got 60% of her money in stocks, 30% in bonds, and 10% in cash. So they give us the returns. On stock was that, and returns on bonds was that, and return on cash was that. So what is the return on a portfolio? So what do? The W is the weight. We take the weight that she's got in stocks, which is 60%, and we multiply that by the return on stocks, which is 8%. And then we add on, right, the weight she's got in bonds is 30%, and we multiply that by the return of bonds, which was there, the 5% there. And then lastly, we take the weight she's got in cash, that's 10%, and we multiply that by the return of cash there, the 3%. And there we go. So that's going to be the weighted mean. Good, not so bad, eh? Right, and now the geometric mean. Well, this is now used when calculating investment returns over multiple periods or to measure compound growth rates. So they ask us to work out compound growth rates. We must always do the geometric mean. So it is a periodic compound growth rate, and this is the formula for it. What we do is we take each and every year's return and we add 1 to it, and then we multiply them all together, and then we put them to the applicable root. But we don't have to worry too much about this, because we're going to just take it, rather look at this one, where we take each and every return, add 1 to it, and then put it to the power of 1 over n, which is the number of years that we've got. And then once we've done all of that, subtract 1. So let's try the example and we'll see how it works. So this is the same example that we did before when we did the arithmetic mean for top tech shares. So now they want us to work out the compound annual growth rate, or the geometric mean. So we take each and every year's return. So the 12%, so to get the percent into decimal format, we just divide the 12 by 100, we get 0.12, we add 1 to it, and we do the same for each and every year, and we multiply them all together. And once we've multiplied them all together, we put that to the power of a 1 over 4, because we've got now here 4 years. So it's, remember it's power, we put it to the power of 1 over n. So we're going to put it to the power of 1 over 4. So there's all our returns, multiply them together. Once we've multiplied them together, we get 1.21. Put all of those to the power of 1 over 4, take off 1. Right, so what we can see, remember, the arithmetic mean, if you go back a couple of slides, we worked out the arithmetic mean, it was 5%. So the geometric mean, it's a little bit less than the arithmetic mean. And this is always the case unless all the observations in the data series are the same. So we must always remember the geometric mean is a little bit less than the arithmetic mean, unless all the numbers are the same. So, and this last point over here, I got this from one of the practice problems. The more dispersed disperse a distribution is, in other words, the more spread out the numbers are, the more volatile the data is, the greater the difference between the arithmetic mean and the geometric mean is. All right, so as we pick up these very important things from the practice problems. So just before we go to the next slide, I just want to say one thing here about this 4.88%, because we're going to say it again on the next slide, but I want to do it twice. So what we can say is that if we earn this, if we earn that 4.88%, compounded annually for 4 years, we would end up with the same amount if we earned 12%, then 4%, then minus 2%, then 6% over 4 years. Okay, so what I've just said there, I'm going to say again on the next slide, and you're going to see why. Because what we're going to do now is we're going to compare arithmetic mean against the geometric mean. So to estimate the average return over a 1-period horizon, it's best that we use the arithmetic mean, because the arithmetic mean, like we've just been through a few minutes ago, it's the average of the 1-period returns. But to estimate the average return over more than 1 period, it's best that we use the geometric mean, because this geometric mean, it captures how the total returns are linked over time. So for example, the rate of growth or return we would have had to earn each year to get the actual performance. So if we go back again, as promised, let's go back to this over here. And now, if we go back to the previous example, this line over here is going to make a lot of sense. So as I was saying, if we had earned this, if we had earned 4.88% compounded annually for 4 years, we would end up with the same amount if we earned 12%, then 4%, then minus 2%, then 6% over those 4 years. Great, so now that is all making sense. So let's take this example over here. We got an investment where returns are up 100% in year 1 and down 50% in year 2. So this is now very dispersed, because we up there the 1 year, then down there the next year. And this is a situation like this, where we've got a great, the data is very dispersed here. So we can expect now the difference between the arithmetic and the geometric mean to be huge. Here, in this example we did, the difference wasn't much. But this example on the next slide, the difference is going to be huge. So let's have a look. So to work out the geometric mean, what do? We take 1 plus each year's returns. And now it's only for 2 years. So we put it to the, once we've multiplied them together, we put that to the power of 1 over 2 and subtract 1. So 100%. So to get rid of the percent side, we divide by 100. So it's going to be 1. And then that 50% there is going to be 0.5. So here we've got 1 plus 1 is 2. I can't believe I've just said that. 1 plus 1 is 2. I've written it down as well, which is even worse. Anyway, we're just having a bit of fun. So 1 minus 0.5 is going to be 0.5. Here we go. So we need to multiply those two together and put it to the power of half and then subtract 1. So 2 multiplied by a half is going to be 1. And we're going to now put that to the power of 1 over 2. So 1 to the power of a half, that is the square root of 1. Eh? Or in your calculator, if you want to check, you can put 1 to the power of half, you're going to get 1. Or the square root of 1 is 1. Subtract 1 is nothing. So, because once we subtract the 1 here, we've got nothing. So to cut a long story short, the geometric mean was 0%. So what is the geometric mean, like we've just been saying? It's the compound rate of growth during the 2 years. It measures past performance. And this is the best way for reporting historical returns. But if we compare this now to the arithmetic mean, we get a totally different story, because of the arithmetic mean, it's just going to be the average of the 1 period returns. It's going to be the average of these two is going to be up 25%. And so we can see now that this arithmetic mean, it definitely distorts the historical performance in quite a big way. So that's just a bit of fun over there for us. Great. So that's the end then of that class. Hope it was helpful. And then we'll see you guys in the next one. Hello, it's Tim here again. I hope you enjoyed the class and found it beneficial. We have some classes available for free on YouTube, but we have classes for the entire curriculum. The classes that are not on YouTube can be purchased from us. If you'd like to purchase the classes, please contact us for the pricing, and I've put our contact details over here. You can purchase all the classes or certain readings that you would like. When you purchase the classes, we provide you with the slides and our notes. I've assisted hundreds of candidates pass CFA exams, and I look forward to also helping you through the CFA program. I've put in 2 testimonials in the slide over here, and we also have a testimonials page on our website that you can review. I look forward to seeing you soon, and all the best.